Hello everyone, welcome once back again to our physics class. Today we are going to start with principle of reversibility of light. Principle of reversibility of light, it says like this: if a ray, after suffering number of reflections and refractions, has its initial path reversed, then the light ray will travel along its entire initial path. This principle we call it as principle of reversibility of light. To understand this, let me take one plane mirror. If I keep a source of light, this is a source of light say, and allow the ray to come and strike the mirror, then you know that reflection will take place if it comes and strikes the plane mirror. After reflection, let us assume that I kept one glass slab, transparent glass slab. Then if it enters inside the glass slab, the light ray from air to glass, if it enters, it will bend towards the normal like this and go. Instead of going straight, it will bend towards the normal. Again, if it comes out from the glass to air, then it will go away from the normal. So here you can see multiple reflection and refraction. The reflection also you can see, refraction of light also you can see at these 2 points. Then this final path, let us assume that CD is the final path. Then in this final path, if I make the light ray to reverse back, then I'll have to keep one plane mirror and see that the ray is coming and striking here normally. If I keep a plane mirror and allow the light ray to come and strike normally, then it will reverse back like this. This mirror will send back the light ray in this direction. If this final path is reversed back, this CD is the final path, reverse back, then it will travel along the entire initial path from where it has come. This principle we call it as principle of reversibility of light. Now, using this principle of reversibility of light, you can prove one relation to prove refractive index of second medium with respect to first is equal to the reciprocal of refractive index of first medium with respect to second. Let us prove and see. For this, we will take two medium. Suppose this is the interface XY separating the two medium. Let us take it as air, the rarer medium, and say water, the denser medium. And mark it as 1 and 2, 1 for air, 2 for denser. If I allow a light ray to come and strike here on the interface XY, let us mark it as AB, the incident ray. Then, following the laws of refraction, it has to bend towards the normal. Now, if I keep a plane mirror here and allow it to reverse back its original path, this should be at an angle of 90 degrees. Then the light ray will travel in this direction. Suppose this point, if I take it as C, earlier it came from A to B and then it went from B to C. By keeping one plane mirror, I am reflecting it back. So it's traveling now from C to B and after that from B to A, following the principle of reversibility of light. So now, if you use Snell's law like this, you can prove it. If or when light enters from air to water, it's entering from air to water initially, then using Snell's law, sin I by sin R is equal to refractive index of water, that is the second medium, with respect to air, that is the first medium. Let us mark this as equation number 1. The same way, when light is reflected back by this mirror, plane mirror, then the light is traveling from C to B, then from B to A. So when light enters from water to air, then here also, if you use Snell's law, you'll get sine R by sine I is equal to, this is angle of incidence, this is angle of refraction. Sine R by sine I, you'll get refractive index of first medium with respect to second. First medium with respect to second. Now, this one, if I take it as equation number 2, and if I multiply them both, multiplying equations 1 and 2, what I can get, sin I by sin R into sin I by sin R into sin R by sin I is equal to, right hand side you have refractive index of second medium with respect to first multiplied by refractive index of first medium with respect to second. Like this you will get it. If you cancel these terms, here one time, then here left hand side will become 1. I'm taking it this side 1. These two refractive index bring the other side. Refractive index of second medium with respect to first multiplied by refractive index of first medium with respect to second. This will give us refractive index of second medium with respect to first is equal to 1 by, or the reciprocal of refractive index of first medium with respect to second. This way you can prove it. This relation even shows that refractive index of first medium with respect to second is not equal to refractive index of second medium with respect to first. This also you can get the idea. They are reciprocal of each other. So glass slab is a transparent medium or a glass block in the shape of a rectangular cuboid. This is your glass, medium 2. Here we'll take medium 1. Here rare medium, here medium 1. If you see the glass slab, here I have one glass slab with me. This is the front face that I am drawing, like this. Now the thickness of the glass slab is measured from here top to bottom. This one we call it as thickness of the glass slab. If I write this as P, Q, R and S, then PQ is called the thickness. This one we call it as the thickness, not this one. Not from top to bottom from here. It is from top to bottom from here. You have to measure. Now if I allow light ray to pass through a glass slab, at this point where the glass slab is, the incident ray is striking the interface PS, suppose this is the incident ray AB, it will refract towards the normal. This angle is the angle of refraction R. This angle is the angle of reflection, angle of incidence I. At this interface QR, again one normal you need to draw. Then this time when light enters from glass to air, it will bend away from the normal. Suppose this is C. BC is the refracted ray and CD is the emergent ray. Here AB is called the incident ray. BC the refracted ray CD, we call it as the emergent ray. The angle between the incident ray and the normal, we call it as angle of incidence. The angle between the refracted ray and the normal, we call it as angle of refraction. Here one more angle of refraction, you can get it. This one. Sometimes it is written as R1 and R2, but both of them will be equal because these two normals, they are parallel to each other. So alternate interior angles are equal. So I am writing here in both the cases R. Now the angle between the emergent ray and the normal, we call it as angle of emergence. We mark it as E. Here I indicates angle of incidence. R is the angle of refraction, and E is. So these are the terms that we use. So what we learned from here is this glass slab, because of placing the glass slab, by how much the light has deviated. Suppose this glass slab is not there, then this incident light would have traveled straight this way. But by placing glass slab, the light is being deviated, and it is deviated by how much you can measure here. If you draw a perpendicular line between the emergent ray and the incident ray, let me mark it as K, CK. This is the deviation that is taking place. We call this deviation CK as lateral displacement. CK is called lateral shift or lateral displacement. So when you look carefully, these two rays, the incident ray and the emergent ray, are parallel to each other. Now the perpendicular distance between the emergent ray and the incident ray, we call it as lateral displacement. Lateral displacement is found to depend upon some factors. So let us see what are the factors. Factors on which lateral displacement depends. These are the factors. Number one, it depends upon this angle of incidence. If the angle of incidence is more, suppose if light ray comes this way, then this lateral displacement also will be more. It depends upon the angle of incidence. It depends upon the refractive index of the glass or the glass slab. It also depends upon the thickness of the glass slab. Thickness T we have written in the diagram of the glass slab. So these are the three factors on which lateral displacement depends. If the thickness of the glass slab is more, lateral displacement also will be more. If the refractive index of the glass is more, refractive index more means more denser. The density is more, very high, then the refractive index will be more, then the lateral displacement will be more. And if the angle of incidence, if you allow the light to strike at a greater angle of incidence, then also lateral displacement will be more. You need to prove that the emergent ray and the incident ray are parallel to each other. Let us see. AB is parallel to, that is, incident ray is parallel to emergent ray, that is CD, or we can write angle I is equal to angle E. if the angle of incidence is equal to angle of emergence, then the two light rays are parallel. Let us check it. When you do the proof, you write it when light travels from air to glass, use your Snell's law, sin I by sin R is equal to refractive index of second medium with respect to first. Second medium with respect to first. Now this one I'll mark it as equation number 1. The next, again, when light travels from, or when light enters from glass to air, when light enters or travels from glass to air, again use Snell's law. Here you get sin R by sin E. So equal to refractive index of first medium with respect to second. First medium with respect to second. Let us mark this as equation number 2. When you multiply them, equation 1 and 2, you will get like this: sin I by sin R into sin R by sin E is equal to refractive index of second medium with respect to first into refractive index of first medium with respect to second. Now, if you look your left hand side, the sin R gets cancelled. So you will get like this: sin I by sin E is equal to refractive index of second medium with respect to first. This one you reciprocate it using the principle of reversibility of light. Then you will get refractive index of second medium with respect to first. Reciprocal. These two you can cancel out, and then you will get on cross multiplication sin I is equal to sin E. Therefore, removing sin from both sides, you will get I is equal to E. This proves AB is parallel to CD. This way you can do it. Some of you may be thinking, if I is equal to E, how AB is parallel to CD? Let us see. Let me draw one diagram here like this. I don't want to make the diagram dirty here. So light is coming like this. This is the normal refracting. Again you are drawing a normal and it's going this way. This is the incident ray. If you extend this normal like this, and this incident ray also, if you extend it this way, you can see here this is I. R has nothing to do, we are talking about I and E. These two are corresponding angles. That's why both the angles are angle of incidence. Again, these are vertically opposite angles. So this is I. After that, if you look, these two lines, the dotted line, the incident ray and the emergent ray, this is a transversal. So these two angles are equal. That means corresponding angles are equal. And if corresponding angles are equal, the lines are parallel. To find the expression for lateral displacement, in our diagram it is CK. CK is the lateral displacement. Let us find one relation. To find this relation, this normal, the first normal, drop it down, bring it down, then it will be perpendicular here. Let us take it as M. This point is C. And this angle with the incident ray produced and the refracted ray, let us take it as del, the angle of deviation. Del, we pronounce it as del, and we are taking it as the angle of deviation. So you do like this. In right triangle BCK, in right triangle BCK, we'll find out sin del. Sin del is equal to, sin is defined as perpendicular to its hypotenuse. This is 90, so opposite of 90 is hypotenuse. It will be CK by BC. CK by BC. Let us take this as equation number 1. Like that, you take another right triangle BMC. In right triangle BMC, you can find out cos R. Now you may think, why cos R? Why not sine? Because if I find sine, I'll get perpendicular by hypotenuse this side. But MC, we don't know what it is. So I'll take cos, because BM I know. This is the thickness of the glass slab. That's why I'm doing cos. It is base by hypotenuse, BM by BC. BM by BC. From here you can find out BC and put it in equation number 1. BC is equal to BM by cos R, and mark this equation number 2. Then put in BC in equation, from equation 2 in equation 1, you can write like that also. Let us put here sin del is equal to CK, and your BC is BM by cos R. Cos R will go up. Now, what we need here is CK, the lateral displacement. So CK will be BM sin del divided by cos R will come down. So your lateral displacement CK is equal to, what is BM? Then this is the thickness of the glass slab. I'll write T. Sin del, what is del? This angle I, this is also angle I, vertically opposite angles are equal. So del will be I minus angle R. Del is angle I minus angle R, and downside you have cos R. So from this relation you can find out the lateral displacement in a glass slab. So now the next topic that we are going to learn is about real depth, apparent depth, and normal shift. Let me take an interface XY. Here let us take it as air, the first medium, and here I am taking it as water, the denser medium or medium 2. You have learned in small classes, this is water. A coin kept in a tumbler appears to be raised up, or in a swimming pool, if you keep, or the base of a swimming pool appears to be raised up. If you look from air inside the water, it appears to be raised up, like that you have learned in small classes. The same principle you are going to use here as well. I am trying to keep a coin here. let this be the coin. I'll mark it as the object O. How light travels, let us see. A light is not from top to bottom. When light travels from the coin, normally like this, on the surface XY, it will go undeviated. Perpendicularly it will go undeviated, it will go straight. Now the second ray, if you draw this way obliquely, then light is entering from water to air. This is your normal, let it be N and S. It will go away from the normal. For making our study easier, I am taking the oblique line with a large gap here. Actually, this point and this point, they are very close to each other, negligible is here. But that time we cannot write down clearly the angle of incidence, angle of refraction. That's why the slanting line is taken a little bit far. Suppose this is A, this is B, let it be C, this is O, the object, and let it be D. So a person looking from here, you keep your eye here and see, then you will feel that the coin has come up, because we take light travels in a straight path. So this is the position of the object and this will be the position of the image. Let me write it as capital letter I. So here if you look the diagram, we are discussing about real depth, apparent depth and normal shift. Here AO is called the real depth. AO is your real depth. AI is called the apparent depth. And IO is called the normal shift. Normally it is getting shifted, perpendicularly it is getting shifted. So we call it as normal shift. We have to learn two things. First of all, to prove refractive index of water. Refractive index of water with respect to air. Air refractive index is 1, we know. When we write refractive index of water with respect to air, it means refractive index of water only. That is equal to real depth divided by apparent depth. So with this formula, real depth here is AO and apparent depth is AI. So these two, if you do the ratio, if you find out this ratio, you get the refractive index of water. This formula is useful while doing practical as well when you will do traveling microscope. So now let us prove and see. In this case, this angle, there is angle of refraction, and this angle, they are forming corresponding angles, so they are equal. And this is angle I, so this angle is also I. There are alternate angles, so both of them will be equal. We'll find out sin I and sin R in the diagram. In triangle ACO, or in right triangle ACO, sin I, you can find out, sin I is equal to perpendicular, that is AC, and hypotenuse is OC. AC by OC. This is 90 degree. Opposite to the angle we call it as perpendicular, and opposite of 90 we call it as hypotenuse. We will mark it as equation number 1. Then in right triangle ACI, in right triangle ACI, sine R is equal to AC by IC. AC by IC. Let us mark this equation number 2. We will divide it to use Snell's law, sin I by sin R. Let us dividing equations 1 and 2. Sin I by sin R is equal to AC by OC, and we are dividing, so if you change the multiplication, it will be IC by AC, so these two you can cancel it out. Now if you use Snell's law, sin I by sin R is refractive index of first medium with respect to second. This is refractive index of first medium with respect to second. This is IC by OC. I want to take reciprocal because I need like this. Refractive index of second medium with respect to first. So what I'll do, if I take the reciprocal, then it will look like this. Refractive index of second medium with respect to first. Then this one also will get reversed. OC by IC, like this you will get it. Now since A and C, as I have said earlier, they are very close to each other, you write down one sentence. Since A and C are very close to each other, OC is nearly equal to, OC will be nearly equal to OA, and IC will be nearly equal to IA. IC will be nearly equal to IA. So we'll replace this OC and IC with OA and AI. So refractive index of second medium with respect to first is equal to, OC is equivalent to OA, and IC is equivalent to IA. And this is your final proof. AO is your real depth. Apparent depth. So if you take the ratio between real depth and apparent depth, then you are going to get the refractive index of the liquid, or we can say refractive index of water with respect to air. To find the expression for normal shift, your normal shift is this one, OY. To find this expression for normal shift, OY, we do geometrically first. OI is equal to AO minus AI. OI, we can write normal shift OI is equal to AO minus AI. AO, if I take common from here, it will be 1 minus, there was no AO, so what we'll do is AI by AO, it will be divided by, so that if you multiply you get AI. Then AO into 1 minus, this one if I do reciprocal, 1 by, if I do, it will be AO by AI. Why I am making like this is real depth, this is apparent depth, this is equal to refractive index. Just earlier you have derived. The AO, suppose the depth of the liquid, let us take it as D, then it will become D into 1 minus 1 by refractive index of second medium with respect to first. This relation you have derived before finding this expression for normal shift. So like this you'll get it. Normal shift OI, it will be equal to the depth of the liquid. If you are keeping on a glass slab here, there will be the thickness of the glass slab multiplied by 1 minus 1 by refractive index of water if it is water and glass if it is glass. Let us solve this equation. A ray of light is incident at an angle of 60 degrees. So you know the angle of incidence I is equal to 60 degrees. On one face of a rectangular glass slab of thickness is also given, that is 0.1 meter, and refractive index 1.5. That means the glass slab is refractive index, that is your mu2, it is 1.5. Calculate the lateral shift produced. You know the formula for lateral shift, it is thickness sin I minus R divided by cos R. This is the formula of lateral shift or lateral displacement. Now here in this question you can see that R is missing, it's not there. So what you do from Snell's law, first of all you find out the value of R. Sin I by sin R is equal to refractive index of glass with respect to air, or simply we can write refractive index of glass because it's mu2 by mu1. Mu1 is equal to 1. So this will become the value. Sin I value is given 60 degree, the angle of incidence. This is sin R is equal to 1.5. Now sin R is equal to sin 60 degree divided by 1.5. Sin 60 is root 3 by 2. 2 into 1.5. This will give us sin R. Now this value, root 3 is 1.732 divided by 15 to the 30, so divided by 3, you will get sin R. Then I'll continue this side. Sin R is equal to, if you divide it, 3 5s are 15. So 0.5 will come first. You can see here this value will come out. 0.5773 you'll get if you divide these two. So sin R, or simply R if you write, sin if you bring this side, then the sin inverse of 0.5773, and its value will be given to you 35.3 degrees. Like this you can find out the value of R first. After that you can approach to your formula for lateral shift. This one, lateral shift is equal to the thickness of the glass slab multiplied by sine of the angle of incidence minus angle of refraction divided by cos of the angle of refraction. Put the value for thickness. You have the value here 0.1 meter. Sine angle of incidence I is 60, so 60 degree, minus angle of refraction is 35.3 degree divided by cos 35.3 degree. This is 0.1 meter multiplied by, if you subtract it, sin 60 minus 35.3 by this given value, you know, is 24.7 degree. 24.7 degree divided by cos 35.3 degree. Now we'll put the values. So lateral shift continuation from there, 0.1 meter multiplied by sin 24.7 degree is 0.418 divided by cos 35.3 degree will be given to you 0.816. On calculation, 0.1, and this point after decimal 3 digit, you remove it, 418. Multiplied by 0.1 will be again here, 1 point will come. Divide by 816. This decimal, if you want to remove it here, 1, 0 will come. On dividing, the unit will be in meter. On dividing, the value will be 0.513 meters. 0.0513 meters. Like this you can calculate. Let us see one more question. See one question from normal shift. Here is your question. Velocity of light in glass is 2 into 10 to the power 8 meter per second. And that in air, generally the speed of light in air and vacuum, we write as C. That is 3 into 10 to the power 8 meter per second. Velocity of light in air is given in glass is given 2 into 10 to the power 8 meter per second. By how much would an ink dot appear to be raised up? They are asking you to find out the normal shift. Normal shift is how much asking? When covered by a glass plate 6 cm thick. So suppose if this is the base of the table, one ink dot is made, and then keeping one glass slab on top of it, then by how much this ink dot will appear to be raised up? This is a normal shift we calculate. So the thickness of the glass slab is given to you 6 cm. Thickness T is equal to 6 cm. And remember the formula, normal shift your formula was thickness multiplied by 1 minus 1 by refractive index of the, if it is glass slab, it will be glass slab. If it is water, if this portion is water, then it will be refractive index of water. Now let us find out what is the refractive index of the glass. Here it is, glass slab. So refractive index of glass, to find out, you will do speed of light in air or vacuum divided by speed of light in glass. So C here is 3 into 10 to the power 8 meter per second, and the speed of light in glass is 2 into 10 to the power 8 meter per second. So these two will get cancelled, units also will get cancelled. 3 by 2 is 1.5. Like this, first we try to find out the refractive index of the glass. After finding this, then you use the formula. Therefore, normal shift is equal to the thickness of the glass multiplied by 1 minus 1 by refractive index of glass. With respect to air, you can write also, if you want to, if you don't want to write, it's up to you. Now put the values. Thickness is 6 cm. This is 6 cm. 1 minus 1 by refractive index is 1.5. Then on calculation, you will get like this: 6. 1 minus 10 by 15. After decimal, 1 digit, so put 1 0 on the top. 2, 5 2s are 10, 5 2s are 15. Then take LCM, 3 minus 2. So it is 6 into 1 by 3. 3 2s are 6, so it will be 2 centimeters. So it will raise up by 2 centimeters. Thank you and have a nice day. We will come back with a new topic again in the next video.